L'Hopital's rule is a rule that we can use to help simplify some limits. So before we go over this rule, go back to what you remember from chapter 2 about limits and evaluate these 3 limit problems at the top of your paper. All right, these shouldn't have been too bad. The first one, when we go to substitute 7 in for x, we don't have any problem. So that's just going to be our answer. I'm going to plug in 7, I get 45 over 9 is 5. Do not expect that to happen on the AP test. That would be very weird if you could just plug in that special value and have no problem. But here in this example, there was no problem, so we got our limit. This next one, when I try substituting in -2 for x, I end up with 0 over 0, which I know is a problem. But fortunately here this expression can be factored. So if I factor the numerator, it cancels out with the denominator and I have a new problem, which is the limit as x approaches -2 of x minus 2, which I can evaluate, becomes -4. And this last one, when I try plugging in infinity, I end up with this fraction, infinity over infinity. So what I do is I look for the terms that dominate. So I ignore that -4 and that +2. And if I just think about the limit as x goes to infinity of x squared over 3x squared, I can see that the x's cancel and I have a limit of 1/3. L'Hopital's rule can't help us with the first problem, but that's okay because the first problem shouldn't take any help. You're just substituting in. L'Hopital's rule can help us simplify limits in cases where substituting in would give you 0 over 0 or infinity over infinity. Those two expressions, 0 divided by 0 and infinity divided by infinity, are two of a class of expressions that we call indeterminate forms. If you have a limit and you substitute in and you get 5, there's nothing unknown. That's the limit. That's totally determinate. 5, it can be evaluated. But 0 over 0, we're not really sure. We can't, if our limit is 0 over 0, we're not sure yet what the behavior is. Same if we have an infinity over infinity. But L'Hopital's rule can help. L'Hopital's rule says, we'll do like the beginning version of L'Hopital's rule. L'Hopital's rule says that if you take the limit of an expression and you end up with a 0 over 0, then if the derivatives of those numerators and denominators exist, then the limit is the same as the derivative of the top over the derivative of the bottom. So probably easiest to explain with an example. So let's do that second example. If I want to take the limit as x goes to -2 of x squared minus 4 over x plus 2, notice in this case f of x is that numerator, so x squared minus 4, and g of x is x plus 2. A is that value that x is trying to approach. In this case, a is -2. So let's just double check. If f of a equals g of a equals 0, so does f of -2 equal g of -2 equals 0? Yes, that's why I have the 0 over 0 problem. Then if f prime of -2 and g prime of -2 both exist, then the limit I'm looking for is just going to be f prime of -2 divided by g prime of -2. So that's going to be f prime of, so f prime is 2x, but I'm going to evaluate that at -2 over the derivative of x plus 2 is 1, and it's just the number 1. It's not a function of x, so it doesn't matter what I'm plugging in. I get the answer -4. Turns out you can use L'Hopital's rule in more and more situations, and we have even this stronger form. If instead of just saying that if the first derivative and the second derivative of your rational expression exist, then the limit is just the first derivative over the second, over the first derivative over the first derivative. You can actually sort of chain these together. So if you take the first derivative and still get 0 over 0, then you could take the second derivative and divide the second derivatives. And if those exist and are not both equal 0, then you have an answer. But if they are both 0, then you could take the third derivative and fourth derivative and keep going. So here's an example from your textbook. If I want the limit as x approaches 0 of 1 minus cosine x over x squared, notice that if I plug in 0, I'm going to get 1 minus cosine 0 over 0 squared. Cosine of 0 is 1, so this is going to be 1 minus 1 is 0 over 0, and that's a problem. But L'Hopital's rule applies. So that's going to be the same as the limit as x approaches 0 of the derivative of the numerator over the derivative of the denominator. The derivative of 1 minus cosine x is 0 minus, cosine is negative sine, so this is going to be sine of x over the derivative of x squared is 2x. When I plug in 0, I get sine of 0 is 0. 2 times 0 is 0. So I still have a problem, but I still have 0 over 0, so I can keep going. That's going to be the limit as x goes to 0 of derivative of sine x is cosine x. Derivative of 2x is 2. When I plug in 0, I get cosine of 0 is 1. And 2 in the denominator. The answer is 1/2. So L'Hopital's rule works even if the limit we're taking is as x approaches infinity or negative infinity. So a doesn't have to be a known quantity. It could be infinity or negative infinity. So watch L'Hopital's rule. Oh, this is supposed to be the third. Oh yeah, okay, the third example. Perfect. So the limit as x approaches infinity of x squared minus 4 over 3x squared plus 2. If I plug in infinity, then I get infinity over infinity, which is a problem. So take the derivative of the numerator and denominator. This is going to be the same as the limit as x goes to infinity of 2x over 6x. Now I can imagine plugging in infinity. I still get infinity over infinity. Let's take the next derivative. This is going to be the limit as x goes to infinity of derivative of 2x is 2. The derivative of 6x is 6. And that limit doesn't depend on x at all. It's just 2/6, which makes 1/3. So try these 3 examples and bring your answers to class. We'll go over them in class.